Okay, welcome to the chapter 10 squiggly notes. This is phasor power. So the basic idea, let's see, we have a voltage signal, we have a current signal, and these guys could be out of phase by something, and then we're going to have a power signal, and it's going to have a phase shift as well, but it's going to have twice the frequency and a few other things about it. But what we're really concerned with, let's say we have some kind of a source, and then we have another load over here, and this has capacitors, inductors, and it might have resistors in here. So what's going to happen when we try and send a power from this source to this load using these AC, this is AC power, using these sinusoidal voltage and current signals, is what's going to happen is that a lot of the power is just going to go back and forth here. It's kind of like a little tug of war. The power goes over here and then it comes back, because these are storage devices, a capacitor and an inductor or storage devices. So a lot of the power is going to go into these storage devices and then bounce back, okay? And that doesn't really do you any good, just to be playing this back and forth thing. So what we're trying to do is do some useful work. So we want some of the work, some of the energy, the power that we're sending over to this load to do useful work for us. We want that to be converted into, heat, basically. And we have a symbol we use for that, which is a P, and it's called the real power that's being converted to some kind of useful work for us. And then you've got this other power that we're still playing tug of war with. And okay, that's the basic idea. We want to know how much is this Q, how much of this power is just going back and forth, and how much of the power is getting converted into useful work. That's really what we're interested in, mostly. There are some other things, like there's a phase shift between the voltage and the current. We're still interested in that, but mostly we're interested in this thing here. Okay, so I'm going to go through these squiggly notes here. Phasor power, so this is Star Trek reference. Got to have that. So first of all, there's P equals IV, right? And we have a time domain signal for voltage. It's it's just the peak, cosine omega t, some angular frequency times time, and then there's a phase shift, right? And then the I is similar, and it has a phase shift. So these both could have phase shifts. Often for convenience, if we're not given a particular phase shift, we'll set one of these to 0, typically the voltage. Okay? So if we're not given one of these or both of these, if we're not given both of these phase shifts, then it's convenient to set one of them to 0. But anyhow, P equals VI, and V is this and I is this. So if you just take these two equations for V and I and plug them into VI and then do some manipulation in algebra, you're going to get this big guy here. This is equation 10.8 from the text. So power as a function of time is all this stuff here, right? Vm, Im. So this is V max, I max, or V peak, I peak. The peak current and voltage values over 2 cosine of the difference between the phase shifts. Okay, so this is there's no time in here, right? This is a constant, right? Because there's no time variable in here. So this is not a function of time. It's just a constant P. And P is the real work that we're interested in. Anyway, there's this, then there's P again, right? Cosine 2 omega t. And then this other thing, which is similar to the P, but it's got a sine in there, and then sine 2 omega t. So yeah, several of these terms are constants. This P, which shows up here and again here, sometimes I'll use the word big P. That's the real or the average power. This is the real or average power, big P, is the power that's doing work for us. That's turning a motor, that's being converted to mechanical energy, or heating up your tea, that's being converted to heat energy, or running your TV set, whatever. Okay, so another thing to note is that the functions of time, the cosine 2 omega t, has twice the frequency. See, for the voltage and the current signal, it's omega t, but for the power signal, it's 2 omega t. Okay, and then because of this constant term here out front with no cosine function with t in it, right? There's a cosine function, but there's no t in here. So this is not a function of time, but over here this one is. But because of this, it's just going to shift p of t up on the vertical axis. Okay, so p can have a vertical shift. P will also have a phase shift. Now the way they write this cosine 2 omega t, there's no phase shift in the cosine term, and there's no phase shift in the sine term. Whereas over here in the v and the I functions, there's a phase shift. Here there is a phase shift in this power term, but because of the way they've broken up this into a cosine and a sine function instead of just a single cosine function, you can't see the phase shift. It sort of hides it. Because remember, there's a cosine and then we're subtracting another sine. A cosine minus sine, right? Cosine minus sine is just another cosine function, but with a phase shift. So they're hiding the phase shift, but it's convenient to look at this p of t in these three forms, with broken up into a constant p term, that constant p term times a cosine function, and then a constant capital Q term times a sine function. It's just convenient. And bottom line, time domain wise, this is what we're looking at. Okay, there's going to be, given V, I, and P, if you graphed all of these, each one of these is V, and one of these little ones here is V, and one of these is I. You can't really tell, but anyway, one of these is V and one of these is I, and they have a shift, right? This signal and this signal have a time shift given by these two angles here. And then P is this other one here with twice the frequency, right? V and I have a frequency omega t, or omega really, and P has a frequency of 2 omega. And then also note that V and I are centered on the axis. That is, they do not have a vertical shift, whereas P has a vertical shift. All right, so you can break it up like this. There's I and V, and then P. P has twice the frequency, and then it might have a vertical shift. Okay, that's time domain. So that's the reason they wrote this P of t time domain in this form, is because it leads to phasor domain. So in phasor domain, we can simplify the time domain equation, and we get this big P term, right? Which was just all of this stuff here, and then the big P term again, and then the Q term. It looks like this: big P, Q. Okay, and our cosine and sine functions. So this is also instantaneous time domain power, but we've just named these big expressions. Over here, this was a big expression. We've just called it big P, and we called the other one Q. So we have names for these things. So P is the average real power, right? This is the power that's doing work for us. It's the average power. If you look at the graph, you can see that it is, in fact, the mathematical average. We also call that the real power. It has units of watts, and it's given by this term. Okay, Q is the reactive power. It's given by this term, and it has units of VAR, or volt amperes reactive. And this is just a way that it's a convenience for when we talk about these things. When you're talking to another engineer, you can just say VAR, and they know that you're talking about reactance. Whereas if you said watts, they'd know you're talking about, the work, the average power that's being done. The real reason why why we're sending power in the first place is so we can get some work out of it. Okay, but still, so watts and VARs, they're both joules per second. There's the rate of transfer of energy. It's just we have different words for that so that we know whether you're talking about average power or reactive power. All right, so to ease into this, let's look at a reactive, an inductive, and a capacitive circuit and what the waveforms would look like. Okay, so if it was a purely resistive circuit, that is a circuit consisting of only a resistor, then the phase shift would be 0, right? Because theta V and theta I would be the same. They would be in phase. They would have no shift between them, which means that the difference would be 0. So cosine of 0 is 1, and sine of 0 is 0. So Q becomes 0. If you look at, so Q is sine of the shift, and P is the cosine of the shift. So if these two guys are in phase, their difference is 0, and basically the Q term drops out. Okay, and P of T simplifies down to this thing, the average power big P plus the average power big P cosine 2 omega t. So it looks like this. It's a sine wave, right? This part here, this P here, is the amplitude of the sine wave. So it goes up big P, and then it comes down big P. But the whole thing, the whole signal is shifted up by P. So that is the average. Big P is the average power. Is this line right here? It's the average. The average of this sine wave is the value right down the middle. So what can we say? So if it was a purely resistive circuit, you would always you'd be sending a maximum amount of power, and then that would drop down to where you're to 0, to where you're sending no power, and then it would climb back up to a maximum and drop down to 0. So you'd be sending power, and then you'd be sending no power, and then sending more power, but you're never sending power back, right? It's never going back. It's all of it's above 0. Okay, the area under the curve is the energy. Yeah. Okay, what if it were an inductive circuit? Then the voltage and the current would be out of phase by 90. Okay, so the sine of 90 is 1, and the P term drops out. The P term up here drops out, and Q is positive, and so P of T just becomes minus Q sine 2 omega t. It looks like this if you graph it. The point here is that you're receiving power, then you're sending power, you're receiving power, then you're sending power. On average, it's 0. The real power, big P, is 0. So you're just doing this back and forth between the source and the load, sending power over to the load and then getting it back and not doing any real work. Likewise, if it was a capacitive circuit, then theta V minus theta I would be minus 90. Sine of that would be minus 1, and this P of T becomes positive Q sine 2 omega t. it just flips this thing upside down. But the point is, for inductive and capacitive, you're still just sending and receiving. It's back and forth, back and forth, back and forth. Back and forth, back and forth, back and forth is the main point. All right. So just to summarize, so for a resistive circuit, you're always, well, that is to say, you're never sending power back. It varies from its peak down to 0 and then up again, but it never goes back. But for Q and for inductive and a purely inductive circuit and a purely capacitive circuit, you're just sending the power back and forth. So in real life, there's no point in just sending power into an inductor and back, or into a capacitor and back. What you're really trying to do is have a resistive load that is converting the power into some other kind of power. But real circuits are going to have some inductive component to them. So a little bit, before we go on, a little bit of terminology. So we have this theta V minus theta I which shows up in several places in equation 10.8. That's called the power factor. And we use the term theta. So theta, it has meaning, right? Theta, it means the phase shift between the voltage and the current. That's what it means, right? And then we have a couple other terms that are useful in discussion. There's something called the power factor. It's just the cosine of the power factor angle. And then there's the reactive factor, which is the sine of the power factor angle. So for the cosine, for the power factor, sometimes we need more information, because the cosine of a given angle is the same as the cosine of the negative of that angle, right? Like the cosine of 30 degrees, whatever that is it's the same as the cosine of negative 30 degrees. So if you're just given a power factor as a number, you don't know if the angle was positive or negative, okay? So you need a little bit more information. So sometimes they'll use terminology like power factor leading. And this is out there, and it's in the industry. For people that work with this all the time, they'll use this terminology. It's in the book. I think it's somewhat ambiguous unless you work with this all the time. Like if you work in the power distribution industry, then you'll have these memorized. But as a student, I find these to be somewhat ambiguous and a little bit confusing. But anyway, just write it down and use it as appropriate. But when they say the power factor is leading, what that means is the current leads the voltage. That means that this is a capacitive, right? ICE, current leads voltage, and theta will be a positive angle, right? Theta will be up. If they use the term power factor lagging, then they're saying that the voltage leads the current, and that therefore it's an inductive circuit, and theta is going to be I had that backwards. Theta is going to be positive, and if it's capacitive, theta will be negative or down. Yeah, I had that backwards. All right, another thing that shows up is RMS values. So, for example, the real power P is given by these two equations. So this is a complex power version of power equals V squared over R, which we saw in DC circuits, and power equals I squared R. We saw those two formulas in DC circuits. So the equivalent formulas for complex AC power are these two, right? Power is V RMS squared over R. It's also I RMS squared over R. So the reason we have these RMS values, and you may remember learning about RMS values in your math class without really an explanation of, well, why Well, this is why. The reason is because in a DC circuit, we have, in DC, I should write that over here. In DC, we have P equals V squared over R and P equals I squared R. For a 100 volt, for example, say it was 100, oops, here's the DC. It was a 100 volt constant DC circuit. We have these two formulas. Should write that over here. V squared over R and I squared R. But for an AC circuit, if you use RMS values, okay, then you can use these two formulas, and it's convenient. But because remember, an RMS value is over here somewhere. There's the peak, right? And then there's the RMS. And RMS is root 2 smaller, right? It's root 2 smaller than the peak, which it may seem to you, this root 2 being somewhat arbitrary, and the math behind it is, we don't really need to worry about it, but the reason for it, the practical reason for it, is so that we can use these two formulas here. All right, so this is why often in AC, like house current, power distribution in houses, domestic power distribution, they often use RMS values so that you can do quick calculations on the power, okay, using these two formulas. Okay, RMS is sometimes called the effective power also. Let's see, so that's terminology. All right, now we can, so we've been talking about mostly time domain, right? We've got V of t, I of t, P of t. This is what those signals look like in the time domain. And then we went through some terminology. Now we can go straight to phasors. So here's the phasor version of complex power, right? Instead of equation 10.8, right? 10.8 is nasty. It's this big old honking thing. We can do this. So S is given by, so the S is a phasor. So the complex power phasor S is given by P, and which is the same P formula, okay, that we had before, the big P formula, plus JQ, and that's the big Q formula, right? And so this is a complex number. It's a phasor with a real power component in watts and a reactive power component in VAR, volt amperes reactive. And S itself has its own unit, volt amperes, or volt amps. Okay, so S is the complex power with units volt amps, P is the real power with units watts, Q is the reactive power with units volt amperes reactive. All of these are joules per second. They're just kind of power, really, but we have different words for them so that we can talk to our engineer colleagues, around the water cooler about stuff, and everybody knows what you're talking about. Like, for example, like a piece of equipment may be rated in volt amperes. That's what might be stamped on the side of if it was, say, a transformer or something, and it's telling you the complex power just by listing volt amperes, or it may list watts, in that which they're telling you the real power. Not always, but, if everybody's doing their job right, that's the way it should be. But of course, it's not the way the world really works. A lot of times people, they don't quite do what they're supposed to do. But anyway, that's the idea behind it. All right, so it looks like this triangle is the relationship between P, Q, and S. Okay, so S is the, the complex power, and its magnitude is something we call the apparent power, which you can get from Pythagoras, right? P squared plus Q squared root. The power factor angle theta is in here, and it's the difference between the voltage and the current. it's the phase shift between the voltage and the current. So let's say a couple of things around here. So only the real power, P, this P component, that's what's doing work for us, right? This P component is the reason that you're trying to transfer power in the first place, because you're trying to, run your stove or something. So that will leave the boundaries of our circuit system. This will be turned into heat. We model that with a resistor, right? But we're modeling it with a resistor, but that's what that really means. What a resistor really means is that you're simulating that electrical energy is being converted to some other kind of energy, heat or mechanical energy or something. Anyway, the reactive loads Q, okay, what they do is, the bigger Q is, the bigger S is going to have to be to get the same P, right? You're trying to send power to some device that's using up P, but there is reactance Q in the circuit, which means some of the power is going back, bouncing back and forth. So imagine, the bigger Q gets here, the bigger S is going to have to be to maintain the same horizontal P, okay? So this is typical with motors, industrial motors, or even little motors in your house. Like most of the reactance in a typical house is inductive because of all the motors you have. There's motors in your air conditioner, and well, that's all I can think of. A blender, anything with a motor in it, a fan. I guess, like things like, well, your stove. If you have an electric stove, it's going to be, if it's a resistive, it's going to be mostly resistive. There's inductive stoves; those have inductance. Something like a microwave, I'm not sure if that's capacitive or inductive. Anyway, so but inductive loads are common because motors, especially in industry, there's big motors and they have big windings of wire, and they have a lot of inductance. So sometimes in industry they'll use these big capacitors to balance out the inductance, and we'll work a problem like that where there's an inductive circuit and you're trying to balance out the power so that the apparent power S doesn't get too big. You're trying to balance the reactive part of the load. Really, ideally, you want to cancel it out if you're trying to maximize power, but we'll talk about that. Anyway, so that's the phasor view of that. Here's some formulas that are good. It's a good point to introduce right now. So you may note that these formulas may seem to be getting more abstract, and that's a legitimate complaint or compliment, depending on whether you're an optimist or a pessimist. But they are getting more abstract, and we do need to take it on a lot of these on faith. The derivations are somewhat involved. Anyway, so P is the V effective, which is, remember, effective is the same as RMS. Anyway, P is V effective, I effective, cosine theta. It's also given by this, 1/2 V max, M stands for max. V max is the peak power. That's the top of the sine or cosine, the peak. V squared over R with a half in there, and then I squared R with a half in there. Those are handy. We also have this. The complex power S is given by the phasor voltage with RMS value in the phasor. The polar coordinate would be the RMS value. The polar magnitude would be the RMS value. And same thing with I. This means conjugate. And that shows up again here. And the reason this is conjugate, it's lost in the derivation. Let me just say that you need a conjugate in here to get the angles to work out with the right sign, and some of it's lost in the derivation. Anyway, here's the relationship between peak value and RMS value. It's just root 2. Peak value is bigger than affected by root 2. Okay, last thing in handy formula-wise is this max power transfer thing. This is the condition for max power transfer for AC, for sinusoidal steady state complex power, or just we say AC, alternating current. Anyway, the condition is the impedance of the load is the conjugate of the Thevenin impedance. Okay, so you calculate the Thevenin equivalent of the distribution circuit. Okay, we're going to do that. You find out what that is. Okay, it's going to be a complex number. So you take the conjugate and set the load equal to that. Which has to do with balancing out this Q. Okay, because you're gonna find the impedance of the distribution part of the circuit, and if the distribution circuit were inductive, it would have a positive Q. So you make the load have a negative Q. You make the load capacitive. So then the inductance of the distribution part of the circuit cancels out the capacitance of the load, and you have a net zero reactance. Okay, so the circuit as a whole, load and source, those two things together, appears to be a resistive circuit. And all of your S, theta will be 0 overall in that condition, and all of your S will be P, because Q will be 0 and theta will be 0. So we'll see that. I'll go through that again in the problems. Okay, one last summary back to time domain, okay? So we've got this phasor power, S, complex power is the real component plus J, Q component. We've got triangle. Remember, this all started with time domain, and that's really, we got to keep an eye on time domain, because me and you humans, we live in time domain, today, tomorrow, yesterday. So let's look at a purely resistive load in time domain. It's going to look like this. P of t is this big P plus big P cosine 2 omega t. It's going to look like that in time domain, going from a max down to 0 and back up again. The average is P, big P. If you looked at it as a phasor, it would have no Q. It would have no Q component. It would just be P. That means P would be equal to the magnitude of S. The phase angle is 0. The triangle is, just flat. It's a line, because there's no angle in here. And V and I are in phase. They may have different magnitudes, V and I, but they're in phase. All right. If it were a purely inductive load, then the time domain signal would look like this, minus Q sine 2 omega t. The power would be going out and then back in for a net of 0. Q would go straight up. So Q would be the magnitude of S. S would just be straight up, with theta would be 90 degrees. And coincidentally, V leads I by 90 degrees. All right, if it's purely capacitive, then Q goes straight down. And I leads V by 90, and the average power is 0. Okay, typically though, the power is a combination of resistive and some reactance, either overall inductive or overall capacitive. It'll lean towards inductive or it'll lean towards capacitive, okay? So it'll be resistive and then some reactance, either inductive or capacitive, along with that resistive. So it looks like this. So P of t is the full time domain thing, big P's and the Q's. The complex power S has a real component and a reactive component. There's a time shift between V and I, or a time shift, or a phase shift if you are dealing with angles. Okay, the time domain signal will look like this. It will be shifted up from the axis by this big P, and that's the average power, shifted vertically from the horizontal axis. It's the average power. But the time domain power will be, changing over time. And like in this case, it's going up to some peak, then down. Now it's going backwards. See, it crosses the axis. And then it comes up again and then down. So for the most part, most of the time, it's sending, that is on average, it's transmitting real power P. But for some of the time, it's sending power back to the source. Okay, so most of the power is going to the load, but a little bit's coming back. On average, though, you're sending real power over. Okay, that's the basic ideas, and I'll be talking about these ideas as I work problems, because that's really the only way to understand these a little bit better. Okay, so I'll work a couple problems.